So what happens if we have two unsymmetrical dienes and dienophiles, as you see here? Then we have many different possibilities for both regioisomers and stereoisomers, and things get pretty interesting. So we can get several different options. Here's my six-membered ring. Let's just put my aldehyde on the wedge for now. And remember that the endo product is generally favored, and that occurs when the electron withdrawing group, which I've drawn, is opposite the inner group on the diene. And so the inner group here are just two hydrogens. So in order to get my inner groups opposite my electron withdrawing group, I need to have the hydrogens that I just drew be dashes. And of course, opposite this hydrogen up here is OCH3. This one down here has another hydrogen, and we can't really tell there. But this would be the endo version. And I should be able to draw the exo version as well. And that's going to be, I'm going to keep everything else the same, but I'm just going to reverse the stereochemistry of my electron withdrawing group. And so now you see that my inner group, the H, is on the same side as the electron withdrawing group. So again, that is the exo version. But what if we flipped the dienophile before we did our mechanism? We would get a couple other versions as well. And so there again, I've just moved the aldehyde down to the bottom carbon. And in this case, I have the electron withdrawing group. It is opposite the missing hydrogen that I haven't drawn here. It is on the opposite side of the inner group, so that would be the endo product. And this would be the exo product. So now the question is, which of these is favored? Which of these is the major product? I should also point out that we can form enantiomers of just about all of these. None of these are meso. None of these have any preference for a certain enantiomer over the other one. And so really I've got 8 different stereoisomeric products here, stereo and regioisomeric products. But one of these we can look at and tell that it is the major product. How do we figure that out? Let's look at lining up our starting materials. And if we look at sort of resonance patterns, we can find that there are some regions of higher negative charge. There are the 3 resonance patterns for the diene, and of course the resonance patterns for the dienophile are like this. And one more. And so the most important ones for us are going to be these last ones. So let's take our let's take those 2 resonance structures and line them up according to how the charges might want them to line up in order to make the Diels-Alder product. So we're going to ignore the charges on the oxygen and just look at the 6 carbons that might make up the 6-membered ring. And you can see that there's a negative charge at the bottom of the diene, right? So this carbon here has adopted a negative charge in the resonance structure that I'm asking you to look at. And if we look at this resonance structure here, the bottom carbon has adopted a positive charge. And so that's this carbon here. It's adopted a positive charge. This carbon here, it has a positive charge. So I'm going to draw these 2 species so that their charges, I'm going to draw them as their original structures, not with the resonance. And of course, when we combine all the resonance structures together, we observe that there's a delta minus at that bottom carbon and a delta plus at this bottom carbon. And so this will be the favored lineup for producing the desired product. And that allows us to discount these two of our possible regioisomers, because you can see here that I'm going to have my electron withdrawing group on the dienophile be right next to the electron donating group on the diene, and that's what my first two products have given me. And then of course I know that the endo product is favored, and so my major product was actually the first one I drew, and it has an enantiomer of course, but that's going to be the major product. All else will be minor product because they won't be formed as much. So you can see here that the transition state shows that our two diene and dienophiles line up in this fashion so that their delta minus charge and delta plus charge are lined up because we know that opposite charges attract. So these partial charges are going to help us line up our diene and dienophile in predictable manners. So let's look at some more examples here. If we draw some resonance in this case, we can find that there's a delta minus on that carbon, and then of course we already know that there's a delta plus on that carbon of the dienophile, so I think we have them already lined up in the desired fashion. And in this case, there is no endo or exo product because we have two hydrogens on this carbon and two hydrogens on this carbon. There's no way for us to see that the electron withdrawing group is away from the inner group on the diene. So there is no endo or exo. There is just this product plus the enantiomer. And we're not going to form the other product that might have, if we flip this dienophile around, we might expect the electron withdrawing group to be added here, but that's not going to be favored again because of this lining up of the partial positive charges and partial negative charges. So this would be our expected major product in red. Let's look at this setup on the bottom of my slide. And we know that we could draw resonance patterns. We could skip a bunch, eventually getting a delta minus charge at the bottom carbon here, and of course delta plus at this carbon. So what I need to do is I need to draw my dienophile like this so that my charges line up. And that tells me how to draw my product. And then of course in this case I observe that there will be a bridging carbons because I have a 6-membered ring in my diene, so I need to draw the bridging structure. So there is my bridging structure, and I have OET right there. And then I know that I want the endo product. That's going to be this product, so that's endo. And I certainly can make the other enantiomer in this case, but the endo is going to be favored along with the product, the regioisomer that has the electron donating group adjacent to the electron withdrawing group. So this would be my major product in this case. And again, I can use the resonance ideas and the partial charge ideas to line up my diene and dienophile in appropriate manners in order to predict what is the major product here.